check it. We'll be looking at a system of first-order differential equations with constant coefficients, and we're going to keep the system simple, usually two first-order differential equations and two functions. So here's an example. Suppose that x and y are both functions of independent variable t. Maybe you have the following system: x minus 2y is equal to x prime, and x plus 4y is equal to y prime. So both of those are first-order differential equations, and but we have two unknown functions, x and y. So that's a system of first-order differential equations, and we do have constant coefficients. Yeah, the things multiplying x and y are not functions of t, but rather constants. This can also be written as a matrix equation. Where we're going to try to solve for x and y, the unknown functions. Now, how this might, why would this be important? Well, if you have higher order differential equations, you can always, well, we can try to reduce those to a system of first order differential equations. So for example, suppose we have a differential equation like this, yeah? Homogeneous. What I could do is I could let x equal to z, and let y equal to z prime. Okay. Then we differentiate x, which of course is equal to z prime, but z prime is equal to y, right? So we have that x prime is equal to y. Now if I differentiate y, I would get that that's equal to z double prime. And because you have a second order differential equation, you can solve for z double prime in terms of the lower order derivatives or function. So z double prime is 3z prime minus z. Okay. Of course, z prime is y, and z is x. So we can say that y prime is right like so is minus x plus 3y. So then we see that that's a system of first order differential equations. Constant coefficients. So what we're going to be interested in is how do you solve such a system? What are equilibrium points? And how do you classify those equilibrium points? Okay. So let's start with so here, let's say we have a matrix of constants. Then we have, let's say, let's call it x. Let's call it bar. Just to remind ourselves that's a vector. It's going to consist of two unknown functions, x1 and x2. So ax is equal to the derivative of x with respect to whatever the independent variable is, say, let's say t, right? So x is really a function of t. And so by the derivative of this vector, we will just differentiate each component function. So what we're going to do is we're going to assume that x has can be solved for in the form e to the power r times t times some vector, right? Let's call that vector v or something. Okay. Well, and v is a constant vector, so v is a constant, so no functions for its components. So we're going to assume that the solution looks like that. Now we differentiate, and of course the vector v is a vector of constants, so we just leave it alone differentiating. Now plug that in. All right, we have a times x is equal to x prime. These positive these exponentials cancel out. And we have that a times v is equal to a multiple of v. And you should all recognize this from linear algebra, right? Where we say that r is an eigenvalue of matrix A, and then v is the corresponding eigenvector, is a corresponding eigenvector. For r, right? So we have, if you'd like, an eigenpair. All right. So it looks like if you want to find solutions of this form, we might want to look at the eigenvalues of matrix A and the corresponding eigenvectors. So let's go through some examples and start classifying equilibrium points. Oh, by the way, I should define that. Equilibrium points are where, if you remember from calculus, the derivative of something is 0, yeah? So if you have a system, these first order differential equations, and you're asked to find equilibrium points, you know that you just set the derivative of your functions equal to 0, so you get ax equals 0 vector. So we want to find solutions. Okay. Right, and then we're going to classify those equilibrium points. And that's going to be based on the eigenvalues of matrix A. Now we're just going to be working with two first-order equations, two functions, so square a 2 by 2 system, if you will. So so we're just going to have two eigenvalues for a 2 by 2 matrix, correct? And so the classification of the equilibrium points is going to be based on those two eigenvalues of our 2 by 2 matrix. Now, since a 2 by 2 matrix is going to have two eigenvalues, not necessarily distinct, you could have a eigenvalue with algebraic multiplicity 2, for example. But we know that for the eigenvalues, there are going to be cases like the eigenvalues are real. Okay. They're real numbers. And you could have, well, you know, they're both negative. See, they're both positive. One is negative, the other one's positive. So these are all distinct real eigenvalues. And of course, we have real eigenvalues or eigenvalue with algebraic multiplicity 2. An eigenvalue can be positive or negative. And then we know that we're going to have the case of imaginary eigenvalues. And for a 2 by 2 matrix, the characteristic polynomial of that matrix that gives you the eigenvalues, whose roots are the eigenvalues, is quadratic. So when we get imaginary eigenvalues, they're going to come in a conjugate pair. The real part plus I beta conjugate. So we're going to be looking at these cases, and also here the cases will be partly classified by whether the real part is going to be negative or whether the real part is positive. Okay, so let's start with our introductory example. So this is going to be where both eigenvalues, just say distinct positive, distinct real positive eigenvalues. So here's a system. We write that as a matrix equation. And if we're looking for solutions that look like some exponential function times a vector, we know that we'd be looking for eigenvalues of our matrix and corresponding eigenvector. Okay, so let's find eigenvalues. So, oh, 1 second. Somebody. Hey.
Hi. Oh, is no one here?
No one's here. I was just recording. So, what are you guys doing? I'm going over a system, but I can, whatever you're working on in class, I can go over. Ouch.
Is this recorded?
Yeah, it's being recorded right now, but I can always switch.
It's okay that we talk.
Yeah, it's fine.
I'm not sure. I know we're doing, last time we were doing like piecewise Laplace transforms, and then there was like impulses. We did Laplace transforms with the little, like the step function.
Yeah.
And then we started talking about impulses.
Oh, okay. So you're not into like series yet, or?
I don't think so.
Homework 9, isn't that about systems of first order differential equations?
I can show you the notes if you want.
Sure. I mean, I think I have the notes.
Oh, you do?
Yeah, are these the ones that are typed up?
Yeah, so I can show you the. Do people usually come to these in person?
Not really.
Do they go online?
Yeah, if they come at all.
Is there something?
No. So, I haven't checked in a while. No.
Oh, wait, I think I had you online for something last semester.
Oh.
I remember
For what class?
for like every class. I remember I asked you, I was like, what's your major?
Oh.
You know everything.
What's your name?
Tien.
Oh, yeah.
Yeah.
Are you in 3351 or no?
3351?
Yeah, no. Yeah, which homework are you thinking about?
My TA at the end of the session was going over. The only thing I knew was impulses.
So, I guess they just posted all the homeworks must not be fair grade, right?
Mm-hmm.
Oh, that's what I was just going, I'm like, dude, they already just finished homework 9. I'm like, behind.
Oh, no.
So that's what I was.
Yeah, only the quizzes and the exams were great.
Well, that's actually really nice. So do you have any, which ones are you thinking about homework 8?
Oh, I think I did homework. Homework 8 is the Laplace stuff, right?
Yeah, homework 9 has some Laplace stuff as well.
I was thinking maybe just mainly homework 9. Because I think homework 8 was okay. You could, I don't know, go over the way to do these problems. Because the lectures, they don't make sense to me. And then this one's pretty good and that makes sense.
Okay, so let's see, let's get the paper with Laplace transforms and these, think about that too much. You don't use the book.
So, no, I don't use the book. Or I have a table if you want.
Do you have an extra one?
I have like 3.
Oh, cool. From the lab?
Just keep doing it out.
Yeah, so we can try homework 9.
Okay.
I'll just record this stuff later. I guess I thought I was. 2420. All right, so you have impulse functions. Okay, so this is the impulse function. So what is the Laplace transform of an impulse function?
What is the impulse?
Oh, that's an even more fundamental question. Yes. Well, you know what the step function is?
Yes.
Well, yeah, so the impulse function isn't even considered a function. It's considered a limiting distribution or something like that. But it has this property. I could derive it for you. It's considered like the derivative of a step function sorts. But I have to go through like a limiting procedure to show you that. But I'll just give you the important properties, right? It has this property that if you integrate a function times the step function, which we think of it spiking at c, because we think of it as being 0 everywhere except at c, where it's like an impulse. And if you integrate over any interval that contains c, then what comes out is just f at c.
I think I remember seeing that.
So that's one of the fundamental properties, and we visualize it as the C. We have a spike, right? And the way they derive this is they actually describe some. It doesn't matter how you look at it, different shapes. But it's a function which is 0 except on a very small interval. On an interval of whatever length epsilon. And it's always defined to have an area of 1. Hence, that's why we call it a distribution. So if the base length is epsilon, then the height would have to be 1 over epsilon. And then we just take a limit as epsilon goes to 0, and that's how we define our delta function. So it's really the limit of something, of a distribution. But using that kind of definition, you can prove that the delta function has this important property. So, for example, if I want to find the Laplace transform of an impulse function that, let's say, spikes at 3, and then this would be by definition this integral over positive numbers of the delta function times e to the negative st. And we integrate out the t's. But by the property above, when this interval from 0 to infinity includes 3. So this should just give you this function evaluated at 3, at t equals 3. So e to the minus 3s. So this is like formula 26 on your Laplace table. And if you have the Laplace transform of the function times its delta thing, then you can imagine that this would just give you it just gives you this evaluated at 3. So that would be f at 3 e to the negative 3s. So just some constant, so it really doesn't matter. Okay. So now let's, and you're already probably familiar with the Laplace transform derivatives of y. Yeah. So now let's, so this also suggests inverse Laplace, right? Usually when you take the Laplace transform of some function, you get something that looks like an algebraic or rational function. Like you have 1 over s minus a, something like that, right? So this is but if you have an exponential, that you have a Laplace transform, you get some sort of exponential, that's because you took the Laplace transform of either a step function or impulse function. So that's important when finding the inverse Laplace here. Okay. So now let's look at homework 9. 1, 2, 3, negative sign. Well, maybe I can just copy it. Okay. That's what I want to use. I'll forget it. I don't need a new app. Okay. All right. So we're going to take the Laplace transform of part A, right? We're going to do part A. So we're going to have the Laplace transform of both sides. And that should be equal. Well, let's see. So then, of course, Laplace transform is linear. So you can just take the Laplace transform term by term. Laplace transform of y double prime, we know is s squared. Big Y, it's a function of s, minus s y naught minus y prime at 0. Okay, that's from Laplace transform of y double prime. Then we have plus 2. And then the Laplace transform of y prime. And plus 3 times Laplace transform of y is just whatever it's unknown, so big Y. All right, on the other side, we have the negative Laplace transform of sine. So so formula 7, if you will, if you don't feel like rewriting this each time. And then plus Laplace transform of the delta function. So we said that that's just going to be an exponential, right, minus this number times s. If you'd like, I'm just using formula 26. All right, so do we have initial conditions? Yeah, of course. We better have for, so y at 0 is 0. So that becomes 0. And y prime at 0 is 0. Well, that's nice. Okay. So this reduces pretty nicely. All right, so now we're in the S domain and we can algebraically solve for this unknown function y. And does that factor? I don't think so. I think that's going to be like heating the square, isn't it? No, you don't like? So if you look at the discriminant here, square root of b squared minus 4ac for this quadratic, I believe that would be 4 minus 12. So yeah, you're going to get complex. So it doesn't factor. All right. So now we divide both sides by this quadratic. Now all we have to do is to recover, y in the time domain by finding inverse Laplace. So towards that end, what do we need to do so that we can recognize a function of s that we can turn back into a function of t? Sure. Yeah. So So let's do the first one. I'll just put -1 up there. Now, we already said that this is an irreducible. Both of these are irreducible quadratics. In other words, they don't factor in real numbers. So do you recall what the form would look like for partial fraction decomposition?
Actually, maybe that, and then ax plus b.
Yeah, so if you have a quadratic factor in the denominator, then you should have a 1 degree less factor in the numerator, so linear factor. So as plus b, and then cs plus d. Okay, we multiply by this common denominator to get rid of it in one fell swoop. And of course, here I always kind of point like I'm tutoring somebody, but we would, when multiplying both sides, you had certain cancellations would happen. And you can stop me if you don't see where these cancellations are coming from. Okay. So we can try to plug in values of s, right, and get a system, or we can just multiply this out. So I guess we'll do that. Let's gather all the s cubed terms. Squared terms. And then all the s terms. And then all the constants. So 3b, and then b. So that should be 10 terms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms. Okay. And that's equal to -1. Right, and then if you'd like to fill this out, we know that if these two polynomials are to be equal for all possible s's, the corresponding coefficients have to equal. So we're going to have that a plus c is 0. Two a plus b plus d is 0. And then 3a plus 2b plus c is 0. And finally, 3b plus d is 0. Well, this is -1, my bad. Well, this would have been a good time to have brought a calculator that, let's see. Easy enough, right? C is just the negative of a. Let's just do it the old-fashioned way. So we can get 2a plus d. Oh, thank you. And then if c is negative a, this just becomes 2a plus 2b. And then we can replace d with negative 1 minus 3b. So let's do that there. So 2a minus 2b is 1, whereas 2a plus 2b is 0. So adding these together, we get that a must be a quarter. Subtracting those would give us that b is a quarter as well. Well, I mean, that can't be right, can it? Negative quarter, oh, yeah, of course, duh. Sorry. All right, and then obviously that would make c equal to a negative quarter and make d equal to negative quarter. Go figure. All right, so anyway, we have the partial fraction decomposition. We can just factor out a quarter, and then we would have as plus b becomes s minus 1. And cs plus d, what does that become? So minus s plus 1. All right. All right, so I bet we can, this is good enough, right, to find the inverse Laplace, at least of this first term. So I can write this as s over s squared plus 1 minus 1 over s squared plus 1. And here in this denominator, I would have to complete the square to recognize what that is from the table. So complete the square. So we're going to take half of that, unless you already know how to complete the square, I don't want to. Okay. So that's going to be, okay. These are really annoying, to be honest. S plus 1. Okay. And there's a quarter there. All right. Okay, so we are going to find the inverse Laplace of the business. So we head to the table, unless you've already memorized the whole thing, or chunks of it. So inverse Laplace of each of these. Oops. Yep, cosine of t, right? And the second one? And this last one? You can use shifting properties, or when you multiply a function by an exponential, you take the Laplace transform. It's like shifts. But you can look at formula 19, for example, right? Sorry, not 19, but 20. Okay. So the inverse Laplace of this business, here we would recognize a as -1 from the table. So we should get e to the negative 1 t cosine, and what is b in this last term? That's right. So voila, yeah. So for the first one, we're good. So next, we'll put it together at the end. So this is, we just did that. So next we focus on the, oh, come on. Thank you. All right, so now we want to focus on the inverse Laplace of this. So it's an exponential. And then what did we have next? We had s. Oh yeah, we had that. So we complete the square in the denominator. Okay. So this should give you a step function. Right. So if you go to if you'd like, formula 27 works. So that'll give you a step function that turns on at what? At c. So at negative 1. No, wait a minute. At 3 pi, right? So you get a step function that turns on. Are you comfortable with talking about step functions?
I mean, are they both similar?
Yeah, there's just different ways of looking at it, right? So for the inverse Laplace, I'd like to look at 27. For Laplace, I'd like to look at 28. I can show you why in a second if you'd like. But you see how this is just e to the minus cs, right? And this is just some function of s. Now I don't have to think about it, like what the function is. I'm going to get a step function times the Laplace transform of this translated by minus c. So, so what does that look like? Right, that looks like some sort of sine. Okay, so that looks like 19. So this is 27. This looks like 19 in the table. So I'm going to get sine of square, forgot my exponential, e to the negative t, because a is negative 1, and then sine of square root of 2t. However, it's not quite right. If you look at formula 27, it says you should be subtracting c from t, right? So subtract 3 pi. So let me scratch. So it's minus t, but t is replaced with t minus pi over 3. 3 pi, no that. And then our cosine, should be sine of b, so square root of 2, and then t minus 3 pi. It is what it is, right? So formula 27.
Did you ask a question?
No, I didn't ask a question. Okay. All right. So, yeah. So I think we'd be done with that one as long as you just put it together for the grader, but yeah. You want to do part B as well? Sure. It looks similar. Do you have something specific in mind? Oh, look, they have the answers. One second. Nice. Except where did they get the 1 over square root of 2? Oh, because you needed, oh, crap. I did miss something, but a little detail that I missed. All right.
I don't know, really any of the rest is when there's like 4 problems, so like 2, 3, 4. I don't really know any of them.
You mean like problem 2, that kind of thing?
Yeah.
All right. So here you're looking at a system of first order differential equations. Oh, froze. So I was working on that. So do you want to do the problem that's on the homework, or do you want to just do the one that I was working on?
I don't know, it's fine. Whichever is easier.
All right. I could have just copied, but I don't know why. Stupid. Silly. Oh. All right. So this is a matrix of we're dealing with a system with constant coefficients. Do you see why this is a system of differential equations, first order? Right. So here, x and y are both considered to be functions of some third variable, independent variable like t. And so here we have x and y involved in the system of differential equations and are first order because the highest derivatives for order 1. And our job is to find what the functions x and y are. And what you can assume is that I'll just write this as ax, the vector, equals x, the vector prime. As for shorthand, that's the way you want to think of it. Or x bar is like the column vector.
What is this? Next one?
So maybe we can, yeah, maybe. So x bar is a vector whose components are functions of the independent variable. And x bar prime is just where you differentiate each of those components. So for short, we write this as a times x, the vector, right, equals x prime. And so what we're going to assume is that a solution will look like this: an exponential function times a vector of constants. So that's just r is just a real number, or sorry, is just a number. I shouldn't say real at all. V is a constant vector. So that's an assumption, right? And let's see what would have to be true about this assumption for us to have a solution of this form. Differentiate x. And v is a vector of constants, so just leave it alone. Now we plug this into our equation. So you have a times x, where x is what we assumed it is. And then x prime, as that's equal to x prime. And so these exponentials on either side cancel out. And you're left with something that should look very, very well. Okay, when did you take linear algebra? Ah, ooh, maybe. Okay, what does that look like to you?
It looks like a lot of things. This whole thing looks very familiar, but
well, what do you call it when you have a matrix times a vector is equal to a multiple of that same vector?
it's something. I remember that.
Yeah, it's like some German eigenvalue, eigenvector. No?
Or I might have read the word but not know how it sounds.
Oh, so let me put R here. So R is, so if you have a matrix times a vector is just simply a multiple of that vector. That multiplier, or that vector is called an eigenvector corresponding to the eigenvalue. So the R is an eigenvalue, just a number.
Oh, can we?
And this is an eigenvector. If you'd like, this is an eigenpair.
Yeah, I just had to work fast online and never had to say out loud.
Oh, okay, okay. Oh, I see. That makes sense. All right. So if we do want to find solutions of the form that we assume, we're essentially going to have to find the eigenvalues and eigenvectors of matrix A. All right. Now, an eigenvector, we say that R is an eigenvalue if there's a non-zero vector, eigenvector, which satisfies that equation, right? And so if we bring this to the other side, this is just a reminder of how to find eigenvalues. And then we pad this with an identity matrix. You know, identity times V is just V. Then we can factor out this eigenvector. We're going to assume that there's a, there's a non-zero vector there, which means that what is true? This means that this matrix is singular, right? If A minus Ri was invertible, then we could multiply both sides by the inverse, and we see that the only solution for V, right? If this were an invertible matrix, you can just multiply both sides by the inverse, and you'll see that the only solution for V is the zero vector. Okay, but we don't want that, right? We want a non-zero solution. So this tells us that this matrix A minus Ri is not invertible, right? So it's called singular. And in particular, what's the determinant of any singular matrix? What did you say? Oh, 0, right?
Oh, sure.
Yeah. Good. All right. So this is the thing. This is what you want to start with to find eigenvalues. So number one, you're going to find eigenvalues. Using that equation. So, okay, so let's do that. So we have the determinant of matrix A minus, I hope I picked real numbers here, yeah, minus R times the identity. And we want that determinant to be 0. So we know that this is just, you're essentially subtracting R from the diagonal entries. Oops. I should have used lambda. It's such a habit to use lambda for eigenvector values. You see? Where I go again. Okay, there's no such thing as lambda. So, oh, that's a -2. All right, so let's compute the determinant. You know how to compute the determinant of a 2x2 matrix? Yeah. All right. So we multiply the business out. Can you see that? And well, luckily for us, this factors. So we get r minus 2 and r minus 3. So we have two eigenvalues, 2 and 3. All right. So now that you find eigenvalues, you're going to find the corresponding eigenspace or eigenvectors, I guess, for each one. So how do you find eigenvectors for a given eigenvalue? Well, it's exactly trying to find solutions to the equation that we wrote over here. So I'll just write that as. Right, so we're looking for some vectors, and some vector that satisfies that equation. So step 2 for each eigenvalue, find eigenvectors. If you'd like, I'd rather say find the basis for the eigenspace, but whatever. All right, so now that let's suppose, and we have to deal with one eigenvalue at a time, r equals 2. In which case, this would become a minus ri becomes negative 1, negative 2, 1, 2. And we're essentially trying to find something in the null space. One of the fundamental subspaces of the matrix. Remember that stuff? Column space, row space?
Yes.
Well, this is the null space, right? The eigenspace, if you like, is just the null space of the matrix A minus R. So we essentially, well, we want to solve this equation, so what we could do is augment our matrix with the 0 column on the right-hand side and row reduce. And then if you row reduce, it's kind of silly that I'm doing this, but now, why is it that I'm always guaranteed to get at least one row of zeros? Right, so if we didn't get a row of zeros, we would get a full set of pivots, if you remember that phrase. So, which would, yeah, okay. Which would mean that your matrix is invertible. If you had all non-zero rows, right, your matrix would be invertible, but by design, by choice of R, we wanted a matrix which is not invertible, so we better get at least one row of zeros when we row reduce. Okay. Right. So here, we're looking for a solution to a system, or this is silly, x1 plus 2x2 should be 0, right? So x1 should be the negative of 2x2. So, for example, we could choose our eigenvector to be 1, negative 2, right? Or, sorry, x2 being as 1, say, and x1 would be negative 2, or any multiple of that, any non-zero multiple of that would be fine. So I might as well, I prefer 2 to negative 1. Okay. All right, well, there you go. We have an eigenvalue, and we found a corresponding eigenvector, so we know that one of the solutions is e to the rt times this eigenvector. That's one solution.
Oh wait, that is the x bar.
That's the very beginning assumption that we're looking for solutions that look like this.
What is the R value?
R is to, I mean the R value is an eigenvalue of matrix A.
Yes.
So then we have to find, we have to go to the next eigenvalue, which is 3, and find the corresponding eigenvector. So we're looking for the null space of matrix A minus 3i. So that would be, what matrix is that? -2, -2, 1, and 1. And then we would augment that. I mean, it just represents the system. So this reduces, I hope you see, to 1, 1, 0, 0, 0, 0. Okay. Right, so this just represents an equation, this first row, that x1 plus x2 must be 0. So x1 and x2 are simply negatives of one another. So we have a good eigenvector here would be, let's say, x1 is 1, so x2 would be negative. So now we have another solution, right? E to the RT times the corresponding eigenvector. Okay. So a general solution then to the original system is going to be a combination of these two solutions. So that should sound familiar. So solution will be some multiple, C1 and C2 arbitrary constants, by the way. Okay. E to the 2t. In other words, we see that x and y as functions of t. X can be thought of as a combination of e to the 2t and e to the, well, hold on, I thought I used the numbers because C1 and C2 are consistent. So 2C1 e to the 2t plus C2 e3t. Do you see how you got that for x? And then yeah. Right, because at the beginning of the day, right, we were trying to find what x and y are as functions of t, and we found a general solution. All right. Now, going back to that problem, we just found a solution by finding eigenvalues and eigenvectors. But really, we could have just found, if for the purposes of what they're asking for, what are they asking for in the homework? Let's say on question 2. What's
Where A is given the two-way matrix x bar to satisfy the indicated initial condition.
Oh, okay.
In addition, classify the type of the origin.
Right. So that's the thing I was thinking about, the origin, right? So they're talking about equilibrium points. In calculus, what's an equilibrium point? Physics, calculus.
Square.
Well, yeah, sure. So in calculus, right, if you have a stable equilibrium, it's like having a marble at the bottom of the bowl. And that would be a minimum, right, for like the parabola. And that would you consider that a stable equilibrium. Yeah, well, that's okay. I'll learn how to spell later in life. All right. And that's a unstable equilibrium. But notice that still the tangent is horizontal. So the derivative of that, if the parabola was some sort of function, then the derivative would be 0 there, right? And so in general, equilibrium, right, means that all the derivatives are, if you have a function of many variables, all the partial derivatives are 0. So it just means derivative is 0 for us. Okay. Because x and y are not changing in some sense if their rates of change are 0. All right, so equilibrium point just means that x prime, y prime is the 0 vector. If you like, x bar prime is just 0. That's what equilibrium point means, right? You want to find a xy pair, which makes the derivative 0. So for our problems where we have a matrix, I already forgot what the matrix was. Where are you matrix? 1, 1, negative 2, 4. Right. If you have this ax equals x prime business, if you want to find equilibrium point, you would set x prime and y prime equal to 0. And then solve for x and y. Where our matrix here, this original matrix A, it's invertible, right? So the only solution is that x and y are both 0. Hence, that's why they talk about the equilibrium point at the origin. So the equilibrium point here is at the origin. All right. And what we do is there's our equilibrium point at the origin, and then we know that x and y are functions of time, so we have what we call a phase plane, where we graph, where we can graph trajectories based on the initial condition. So we can graph the curve x of t, y of t. It's a parametric curve essentially, right? So if you have an initial condition, you start somewhere, and then as time evolves, you have some sort of trajectory. So you get a path in space. Now, we know that this is an equilibrium, okay? Now imagine, what's unstable and what's stable equilibrium? Well, a stable equilibrium is one where you can get perturbed a bit. You can move this marble up a bit, but it'll roll back down to the equilibrium position, right? So things tend to return to this stable equilibrium. They get perturbed a little bit. But for an unstable equilibrium, if you perturb this little particle a little away from the equilibrium, it'll go away from the equilibrium point and roll down the hill, right? So stable equilibriums are where the trajectories will tend to go towards the equilibrium point. Right? So depending on some initial condition, you start somewhere in the plane. And if you have a stable equilibrium, the trajectories will tend to go towards that stable equilibrium. And if you have an unstable equilibrium, if you start somewhere, well, there's many ways to be unstable, but and the idea is that you'll be tending to move away, right? You'll be moving away from the unstable equilibrium. And sometimes we have to learn how to classify these based on eigenvalues, but sometimes it's unstable because you just kind of tend to spiral away, right? But you're still moving away. And there's a third case. It's kind of like this case. This is an equilibrium point. The derivative would be 0 with a function. But is it stable or unstable? I just drew this graph like.
We could go either way.
Yeah, we call that a saddle. Right. So a saddle would look something like this. If you start somewhere based on initial condition, your trajectory based on the system of differential equations can take you near this point, but as you move towards it, then you slowly veer away. So your trajectories will kind of be going towards it from one direction, but away from it in another direction. So that's called a saddle. So it depends if we were, yeah. All right, so how do we know? Well, if we have a solution to the our equation, let's write it down again. You can kind of think of these as if you draw the phase plate. You can draw these eigenvectors, let's say, at the origin, which is our equilibrium point. So 2, -1. It doesn't really matter what it looks like. And 1, -1. Yeah, it doesn't matter, whatever. But these kind of become like leading lines. And what would happen as time goes on? Okay, as t gets large, what happens? Well, would these vectors be getting larger or smaller? Larger, because that's an exponential that's growing, right? Exponential growth. So what happens is as time moves on, also based on the constants there, but that's based on the initial condition, you'd be moving away from the origin. So I'm going to use colors because they tell me to. All right. Come on. So where you start depends on the initial condition, but you would tend to move away from this equilibrium. So that's an unstable equilibrium point, and we call that a node. So there should be a somewhere summary of all the names. And I had it open. A summary of I was just looking at. I don't know what it is. I just looking. I guess he's. equilibrium, so no. All right, it's an unstable node.
Okay.
I'm pretty sure. All right, we'll find it. We'll find it in a second. All right, it's an unstable node. So the thing is, you didn't have to find the solution to know this. It's always based on the eigenvalues, and it's the real part of the eigenvalues, suggesting that you have imaginary eigenvalues. So that's not going to be fun, but okay. So notice that both our eigenvalues for matrix A were positive, right? The eigenvalues were 2 and 3. And so that suggests, because of this exponential, that as t goes on, your vectors are getting larger, you move further away from the origin. So in the case where the eigenvalues are real numbers, and both positive, I'll just say that way, then you're going to get an unstable node. Node because you're like moving away, like radially away from it. All right, so now imagine that we have this system. Right, and if you want to find solutions, you would need to find eigenvalues, eigenvectors. But if you're just looking for, classifying that equilibrium point at the origin, all you would need to do is find the eigenvalues. Right? So let's see what. So here, let's find eigenvalues. Let me zoom in because. So we're going to look at this equation, determinant of our matrix minus Ri should be 0. So you have matrix A, and then you essentially just subtract R from the diagonals. So we compute the determinant. We get R squared. What the heck did I do? Oh, I know. -1. Yeah, so we get 5 lambda, or 5r. And then -6 plus 10. All right, good. Right, so in any case, we can factor, and then we see that both our eigenvalues are real numbers. They're distinct and they're both negative. Okay, and then we can find eigenvectors to find solutions, but since we're almost out of time, I'm just going to say that the solution would look something like this, the general solution, a multiple of e to the r1 times t times some eigenvector, right, corresponding to this eigenvalue of -1. So I don't know what that chunk would be. Plus, but it's non-zero in any case. Times some eigenvector But again, if we have obviously a equilibrium point at the origin, because that's if x and y are both 0, the derivatives are also simultaneously 0. You can draw these eigenvectors. They really don't matter what they look like. If you're tracing trajectories, like if you have initial condition, you kind of have a sense of how the system progresses in time. Then these would be the eigenvectors give you like guiding lines. But now notice that if you start somewhere and t starts at 0 and goes to infinity, what happens to these vectors? Where do they go as t goes to infinity? What's the limit as t goes to infinity of e to the negative t? Oh, that's a decaying exponential, yeah. It goes to 0. Like, think of that as maybe, if you don't recall, like that. And so as t goes to infinity, e to the infinity goes to infinity, if you will. And 1 over big is small, so that goes to 0. All right, okay. So the limit is 0. And likewise here, because this is a negative coefficient, this vector would go to 0 as well in the long run. So here we're all just starting at some initial point. We'll all be heading towards this equilibrium, right? So this is stable. So we call this a stable node. And I guess I'm going to have to finish up, right? Because you have other cases. You have to consider that your eigenvalue, one eigenvalue could be positive, the other eigenvalue could be negative, and assuming they're real, what would that be? So suppose we have a positive eigenvalue and a negative one. Okay, so our general solution would look like this is negative eigenvector, and this is positive eigenvector. Right. So if you look at the phase plane, and again, suppose you have an equilibrium at the origin, and you have two eigenvectors. As t goes to infinity, what happens to this vector? It goes to 0, right? And as t goes to infinity, this goes off to infinity because you have a growing exponential as opposed to decaying. So what would happen is that if you start somewhere, you would kind of go to 0, but then as time moves on, this would take over, if you will, and just go like that. So if you have real eigenvalues, but one is negative and the other one's positive, we call that a saddle. And it's inherently unstable in the sense that whatever, you might approach the equilibrium point for a while, but eventually will veer away. And then you have two negatives, two positives, one negative, one positive, right? You still have to consider what happens if you have real but repeated roots. And you have to consider what happens when you have complex roots. Much time. Yeah, so for the purposes of the homework, suppose your roots are complex, and because we're dealing with a 2x2 system, those will always come in complex conjugate pairs if you find the eigenvalues. And so that your solution would look something like, and this is rather a simplification, but alpha t, and then you get e to the I beta t. So this will give you a sine and a cosine, right? Times some eigenvector, which is probably complex. It might be complex. And then your conjugate is also a solution. So this would give you some more sines and cosines. What's important is that those oscillate, right? But if alpha is negative, so the real part of your complex eigenvalue, if it's negative, then both of these are decaying exponentials, right? E to the alpha t goes to 0 as t goes to infinity. And this rest of the stuff just keeps oscillating. So what happens is that you get a spiral going. Right? You start somewhere, and because of the cosine and sine, the oscillating part, you kind of spiral. And then because you have a decaying exponential, you spiral towards 0. Okay, so we have an equilibrium. It's what we call asymptotically stable. As t goes to infinity, we approach d. So this is a spiral, and it's stable, but it's asymptotically stable. And they might even at some point ask you, which way does this spiral, clockwise or counterclockwise, or something like that. Now, if, on the other hand, the real part of your complex eigenvalue is positive, then what happens? Then e to the alpha t goes to infinity as t goes to infinity. So it's still a spiral because of the oscillatory part, sines and cosines hidden there. But you'd be then moving away from the equilibrium. So you're spiraling away from the equilibrium point, so that's a spiral, but it's asymptotically unstable. It's just unstable, I guess. And if the real part is 0, what happens? Well, then you just have oscillatory, just sines and cosines. So what ends up happening is this is 0, and you have neither a descent towards the equilibrium nor a ascent away from the equilibrium, right? So we have an orbit. I don't know what they call it, but it's an orbit for the third case. That's why we've had the book. So orbit, because you're just going around. Once you start somewhere, you never go to the equilibrium point. You just keep kind of orbit like a planet or something.
So is that like either stable or unstable?
Well, it's considered stable in some sense because you're stuck there.
Yeah.
It's a stable orbit. I just forget exactly what they call it. It's not a spiral, obviously. We'll have to see. And okay. Anyway, that's it. I gotta go downstairs. Are you gonna join us downstairs at some point?
Like history?
Yeah.
Thank you.
Sure. I'm glad somebody